So, welcome everybody to our iPHA Q&A series with the Passivhaus Institute. Today, I welcome Jürgen Schnieders from the Institute to talk more about the Research and Monitoring Department. Also with us is Jessica Grove-Smith, who will monitor the chat and help to answer questions in the chat. Georgia Zar, my colleague, she is going to be with us, hopefully. She's having internet problems at the moment. And my name is Karl Halbach. So welcome, everybody. Jürgen, could you? Yes, perfect. Thank you. So a quick look at our agenda. We will have the introduction, what I am doing right now. Then we will hear a presentation about Passivhaus research and monitoring. And after that, as always, if you have attended before, you know that, we will have time for questions and answers. The session will run about an hour. That's what we're aiming for. During the webinar, you can, I already see you are using the chat box to say hi. That's great. You can type in your questions and we will collect them and get to them after the presentation. This webinar is also being recorded and you can get you can watch the replay after the event. It will be sent out automatically. Okay, so this again is the team. My colleague, as I was saying, will probably join us later. And yes, if you want to reach us, you can contact us at info@passivhausinternational.org, or you can visit us on our website. Okay, and now to our presenter, Dr. Jürgen Schnieders. He is the head of the Training and Professional Certification Department at the Passivhaus Institute. He is a physicist and a senior scientist at the Institute, and he has been working for quite a while at the Institute now since 1997. He's also one of the key key developer of the algorithms in our Passivhaus planning package, the PHP. I hope a lot of you work with that. And he has a long-lasting experience in consultation for all kinds of Passivhaus projects all around the globe. And last but not least, he evaluated the monitoring data from more than 100 Passivhaus dwelling units with the CEPEH-EUS, the cost-efficient Passive Houses as European Standards project. And without further ado, I hand over to Jürgen to tell you more about the training.
So thanks for the introduction, Karl, and welcome everybody to the session. We will be, or I will be talking about research and monitoring that we are carrying out at PHI. The Passivhaus Institute was founded in 1996, and the main goal at that time was actually to develop an independent institute that would bridge the gap between researchers and building professionals. So some researchers knew relatively well how energy in buildings is working, how its efficiency can be improved, where the leakages are, where the energy is going, and how we could possibly build highly efficient buildings. But not many building professionals knew that. So today we have different branches that are, for example, providing building certification and consultancy in this field, doing that in the field of component certification, so window frames or ventilation units. We are doing training and education. We are developing Passivhaus tools, which is already closely linked to what is at the heart of all these activities, namely the actual research that provides us with the knowledge that we are trying to spread, including in this webinar. So today I'm trying to show you how this research is taking place, what we are doing there, how we are doing it mainly, and also what the types of results are. And of course, this is a Q&A session, so in the end, we will hopefully have lots of questions to answer and things to discuss. So one of the things we are doing in the field of research is monitoring, and monitoring can be can relate to very different fields. Much of what we do is field measurements, so we are actually monitoring buildings that are inhabited, where we can see how the buildings are performing. And we get, for example, such a diagram that shows for 32 dwelling units, identical or nearly identical terraced houses, the heating energy consumption over 3 years. And we see that there are quite large spreads between those that consume very little and those that consume very much. But on average, we get very close to what we are predicting with the PHPP calculations. So these are important results. We are also doing blower door tests. We are checking, for example, how such a wooden beam can be connected to the airtight envelope without leakages. This box here contains plugs that have small electricity counters in them so that we can measure the electricity consumption of different household appliances. And weather stations also form part of what we are measuring if we are looking at the performance of a certain building. Usually it's not only about doing monitoring, but what is important is to understand what's going on. So we need monitoring results on the one hand, but we need an understanding of what happens on the other hand. So one example is this school which you see here, which was built in Frankfurt. The photo is actually a model that was used for an architectural competition. The building is placed on a slight slope, so designers did not want to place insulation below the floor slab because at that time they were afraid that the building would start to slide. They didn't want to put it, or we didn't want to put it on top of the floor slab either in order to avoid all the thermal bridges. So what the final result was, the final decision to have insulation a little on the floor slab and also at the sides of the building, so that we would get a warm piece of ground below the building where heat losses are reduced. And in order to make sure that this approach is actually working, we were burying some temperature sensors under the slab in different points. And then the building was built, and then we successfully found the cables of that sensors and connected them to the monitoring system. And monitored for 5 years because the processes in the ground are evolving very slowly. What the temperatures do, what the heat losses, the heat flows in certain points in the floor slab are, and if that is in agreement with what we are calculating. And after taking into account the groundwater flow that was taking place here to a spring down a few hundred yards, we actually got very good agreement. So we are confident that this type of reducing insulation under the floor slab and putting it at the side instead is actually working. Another example is down here, one of the first passive house office buildings, which had a passive cooling approach that was mainly consisting of night ventilation. So they would open windows automatically during the night And in the floor plans, there are big openings that allow the air to enter the building on the ground floor and then go up and leave the building on the top floor, creating a strong draft and high air change rates. And we had measurements available of the temperatures in the building and of the outdoor temperature and of wind speed and direction, and put that into a coupled simulation of thermal simulation on the one hand side and airflow simulation for multiple zones on the other hand, in order to find if our models for airflow in the building for night ventilation are correct and can reliably be used for design purposes, which in this case turned out they did. Here on the right, at the bottom, you can see measurements for window temperatures. That was from one of the first research projects, even before the Passive House Institute was founded, from the first Passive House in Darmstadt-Kranichstein. We see that around noon, when the sun is shining onto the glazing, the temperature of the interior glazing is rising to 30 up to 35 degrees, so that actually the interior pane turns into kind of a radiator, bringing heat into the room. And the calculated temperatures of that glazing are in very good agreement with what was measured there. The calculation in this case was carried out by the DUNBIL program, which is a dynamic building simulation program, similar to, for example, Energy Plus or Transys or EDA-ICE, which has been developed and is still being maintained at the Passive House Institute. Originally by Wolfgang Feist back in the 1980s. These types of programs are important because they are close to physical first principles. So we can be relatively sure that if we look at some kind of new strategy, a different climate, a different way of storing heat, say phase change materials, for example. If we investigate these by using dynamic building simulation with DUNBIL hour by hour, we can predict how the building is behaving without having to build it and to run experiments. But of course, we need to be sure that the programs are actually representing reality correctly. There could always be coding mistakes in them or physical effects that were overlooked in developing the model. So it is important to validate these programs to make sure that they are working properly. And then they are the method of choice for performance prediction of buildings, but also for developing design tools, simplified tools that are easy to handle, that are working faster, for example, the PHPP, which is relying on lots of comparisons for different cases with the DUNBIL program, which in turn is linked to detailed monitorings so that we get confidence into the results of the design tools. Let me show you a few results from this first passive house in Darmstadt-Kranichstein, which was first inhabited in 1991, where this DUNBIL validation has been carried out. So what we see here is an exterior wall with some masonry, limestone in this case, and an exterior insulation. Here, sensors were installed that would measure the temperature on the interior surface and at the boundary between the insulation and the masonry, and somewhere in the middle of the insulation and on the exterior surface. And on the left-hand side, you can see how these temperatures are developing over a few days in mid-October. So the exterior surface becomes warm if the sun is shining onto it, much warmer than the ambient air. And during the night, it gets colder because of radiation, infrared radiation into the cold sky. At the center of the insulation, we have slightly higher temperatures, and at the inside, it's the temperature is nearly constant at about 24 degrees in this case. So the points in this diagram are monitored values, measurements, and the lines are calculated. And so we hardly can distinguish the two. There's a difference of no more than 0.2 Kelvin, about 0.3 Fahrenheit, between calculation and monitoring, which gives us a lot of confidence into the performance of these models. As I said, the building was first inhabited in 1991, and 25 years later we had the chance to do some research project that would ask the question, is passive house, are the strategies that have been followed here a long-lasting solution? Does the building still perform as it did in the beginning? You might say, well, sure it does, because we know the gas consumptions for space heating, so directly measured how much gas is going into the building in order to provide heating. And this was, well, in the first year it was a bit higher. On the left-hand side, that's an ordinary building or a low-energy building whatsoever. In the first year, not all the insulation was properly installed. The building was not fully finished. But afterwards, for more than 20 years, the heating energy consumption is extremely low, and there is no tendency seen here that it would increase. An average of 8.5 kilowatt hours per square meter per year was measured here. The PHPP would predict 10.5 kilowatt hours per square meter and year. So it is slightly conservative as you would desire it from a design tool. So from the gas consumptions, we can say that apparently the building is working after 25 years as it did in the second year without any deterioration. Now, we wanted to know that in more detail, and did, for example, another blower door test. So what we see here are blower door test results in the beginning and after 1 year, after 3 years, after 8 years, after 10 years, and again after 25 years. And there are, of course, variations. So there is a certain limited accuracy of a blower door test, of course. But after 25 years, we still get an extremely airtight building, which has the same N50 value as it had right after it was finished. So that's an important result from research, from monitoring, that the strategies that were followed in this building for making it airtight are durable, are long-lasting, are still working after 25 years as they did on the first day. Another result from that project shows the roof. This roof construction might appear a bit critical because it has a watertight and obviously also vapor-tight layer here on top. So any humidity that by diffusion is entering the roof construction could go up and would be stopped here at the vapor barrier and at the watertight layer. And usually it would dry out during summertime because the roof is heated by the sun that's shining onto the roof. But now we also have a grass roof, which is evaporating water so that it is cooler. And the question is this construction durable? Does it really last? So temperature and humidity sensors were installed in 5 different places. The results tell us that the maximum humidity that was achieved in this construction was 91%. Now, 91% sounds maybe a bit close to 100%, but in fact it means that we have a water content in the wood construction of less than 14% mass, and up to 15% there is absolutely no problem, so that we can conclude this construction is simple, but it's durable. It lasted for 25 years without accumulating humidity, and we may assume that there will be at least another 25 years of useful life for this construction with a U value of 0.1. We did these types of monitoring in varying detail for a large number of buildings. A slightly rougher monitoring it was a lot rougher actually, was carried out in the Bahnstadt area in Heidelberg, a large passive house development with about 90,000 square meters of living area. There were different building blocks, building fields, which are shown here in the bar chart. So the heating demand is varying between the different building fields. We also have an idea why it is varying and why it is a bit higher in one case and lower in the other case. And in addition, we can say that on average, we are close to the passive house limit. We have approximately 15 kilowatt hours per square meter and year heating demand measured in this large development, so that we can say we don't need scientists to be involved in developing passive houses and passive house details. Every designer can do it and can successfully realize these buildings. Another important result from doing this research. In the last years, we are pushing frontiers to different building typologies. So a design project for a hospital has recently been finished, and we are now going to do monitoring there. Hospitals, supermarkets, swimming pools are different from residential buildings in that the main energy consumption is not heating alone, but there are other energy consumers that are relevant. For example, in a supermarket, we would have refrigerated display cabinets, which consume more than 50% of the total energy that is used in a supermarket. And it turns out that the waste heat from these display cabinets is enough to heat the supermarket even on the coldest days. So we don't need an additional heat generator, for example, a gas boiler or something, if we have a appropriately designed building envelope. And still, it is important to aim at maximum efficiency of these refrigerated cabinets and of the cold generation, much more even than looking at airtightness and insulation of the building envelope, because this electricity consumption is much more important for the total energy consumption. Something similar holds for swimming pools. In swimming pools, there is evaporation from the water into the air, and this evaporation takes up a lot of energy. So we investigated in research projects what the actual energy flows are and how they can possibly be reduced. Could we, for example, increase the humidity and interestingly also increase the temperature of the air in order to raise the vapor pressure of the air so that there is less evaporation and less energy needed for heating the water, for compensating for that evaporation. If we use passive house components, highly insulated windows, for example, where the risk of condensation is reduced even at higher humidities. We tried if heat pumps could make use of the evaporated water from the exhaust air, which at least in practice turned out not to be very successful. We also focused on pumps and water treatment, which is a large energy consumer. So there's different topics apart from heating that need to be addressed if we want to build highly efficient non-residential buildings. Two more research results just to show what different fields we are working in and how the approaches differ. Primary energy has for a long time been the way to judge the efficiency and the environmental impacts of buildings. But primary energy starts to become a moving target when electricity production changes, so that the primary energy factor for electricity is dropping from year to year. And in the long run, it will become totally meaningless. But still, it is important to have highly efficient buildings. And why this is the case can be seen if we look at how energy will be produced in the future from renewable sources. Because not all the renewable electricity can be used right away. Some of it needs to be stored for a few days. Some of it needs to be stored from summer to winter. And during these storage processes, losses occur that somehow need to be accounted for. So electricity that we are using for heating requires much more primary renewable electricity to be produced than, for example, electricity that we use for cooling. Because cooling will mainly be required when the sun is shining, when it's hot, when we can easily produce electricity from photovoltaics. And there may be a need to store some of it for a few hours, but most of it can directly be used. And we need to add less additional PV than we would need for higher heating demands. This is reflected in these primary energy renewable factors, PER factors, that for the example of Germany are about a 1.8 for electricity for heating, but 1.1 for electricity for cooling. And for domestic hot water, household electricity that are required all year round, it's somewhere in between. So an important research result that allows us to judge different building strategies, different concepts of how a building could be designed with respect to the future energy system. A question that arose some years ago was how vented drain pipes affect the energy balance of a building. Now, this is a good example, and that's why I'm showing it here, for how this whole process is evolving. First of all, we try to understand what the governing principles are, what is happening here with the air that is passing through the drain pipes. Cold air from the ground would enter the building, and by the stack effect, it would be heated up and would be drawn up and released above the roof, which can theoretically be addressed and gives us this exponential equation here. So where we see that what we would expect from our understanding at that point of the processes in the building gives us this curve. So here's the height of the building, up to 40 meters in this example, and here's the temperature. We enter with about 8 degrees, and then the temperature is rising as the air rises up in the building. But this rise obviously comes to a saturation the closer we get to room temperature. So if we have a very high building, it will probably not make much of a difference whether this drain stack is insulated or not, whether we try to reduce the airflow in there, because the air that is passing through the stack will be warm in the end of the day anyway. Now, once we have an idea of what is happening there, we need to verify that. So we had the chance to install temperature sensors and also heat flow sensors in ventilated drain pipes, one for rainwater and one for wastewater. And on the left-hand side, down here, you can see you can see the temperatures in that drain pipe depending on the ambient temperature. In principle, what happens would be expected. If it is warm outside, it will also be warm. The air that is entering the stack will be warmer. And in colder periods, we will have a higher heat flow because we have lower entering air temperatures. But then there are some points up here, and these could be identified as rainwater running down the pipe, which is, of course, cooling the pipe from the inside, so we get a higher heat flow. And it only happens if we have ambient temperatures at or above 0 degrees centigrade, because otherwise there would be snow and no water would run down the drain pipe. And by evaluating all these hourly measurements here, we could develop a model that takes all these effects into account, that led to the result, for example, that these rain occurrences appear in the chart, but they don't have a significant influence on the heat loss, so that they can actually be neglected. And that led to a calculation tool which becomes part of the PHPP and allows us to numerically evaluate the effects of a certain drain pipe system. So this type of research, as you may expect, is expensive. It takes weeks of work, months of work to get a monitoring system up and running. It needs to be kept running sometimes for several years. You need to evaluate all the results, add calibration factors, repair broken sensors, develop different models and check if they agree with the measured data. So we can only do that with support by some public entity, for example, by the European Union, by governments of the federal states. The state of Hesse, for example, has been highly supportive of the passive house development. They were very important for us. Just a few examples, funded projects by the European Union. The most important one and the first one is CFIUS, cost-efficient passive houses as European standards. Several hundred dwelling units were built in different European locations and were monitored, and the monitoring results for the first time proved that passive houses can be built not only as scientifically accompanied demonstration projects, but on a larger scale by ordinary designers, by ordinary craftsmen, really having the chance to become a standard. And then there was, for example, the PEP project, Promotion of European Passive Houses, and the Passive On project, both of which aimed at taking this experience from Central Europe to the rest of the continent. There was the Eurofit project, which was about step-by-step retrofits. We had PASREC, which aimed at passive house regions, including renewable energies. And the recently finished project was called Sinfonia, which dealt with ambitious district refurbishments on a larger scale. There's one ongoing European Union project right now, which is called Outfit, where we are again dealing with retrofits and where we are still looking for building projects, retrofit projects, particularly those that are interested in serial renovation with prefabricated elements, in order to have these processes optimized and to develop strategies that would allow to do that on a large scale in order to more quickly move to a climate neutral building stock. We have always been aiming to distribute the results of our research, for example, on our website. So you can find lots of reports here under Literature and Tools on www.passivhouse.com. Passipedia, of course, is an important resource for research results. We try to get all important information into Passipedia. And the annual International Passive House conferences are sharing knowledge not only by PHI, but also results developed all over the world by scientists, by builders, by designers. So giving you first-hand research results for building practice. So that's about it. Further information can be found at passivhouse.com, at passipedia.org, at passivhouseinternational.org. And I am now happy to hear your questions and hopefully give some answers.
Okay, perfect. Thank you, Jürgen, for this very detailed technical overview. We will play our video for like a minute to give you room to breathe and maybe drink a sip of water. And we'll be right back to start with the questions. Okay, and we are back. Can you hear me, Jürgen?
Yes, I can hear you perfectly.
Oh, there's Georgia. She fixed her internet.
I did. Welcome to my hallway.
That's great. Okay, let's get into the questions. Louis asks in regards to the, I think it was the office building in the beginning of your presentation, regarding the data results for the temperatures during the summer. I'm assuming this building is in use in summer, and how did the data fare with like hot temperatures?
Yes, of course, the building is in use in summer, and that's why they had this night ventilation strategy, and it performed very well. Also due to the fact that it was not in the hottest regions of Germany, so that's a central German climate that has, I would say, maximum temperatures during the daytime of 30 degrees centigrade if you have a warm day. So nighttime temperatures would drop to less than 20, rather to 15 degrees centigrade. And there's no humidity problems either, so night ventilation is a very appropriate strategy in that case, particularly if you combine it with limited interior loads. So that was actually working very well. And we learned a lot about how it works, that our calculation models are correct, at least for this building, and that gives us more confidence if we extend the models to other climates.
Perfect. That's great to hear. Richard asks, in regarding to the monitoring equipment for passive house buildings, is there a recommended set or sets of equipment available that we can purchase to carry out the monitoring with Wi-Fi or a LAN connection? Sorry.
So nothing special I could recommend. Maybe the people who are doing the monitoring at PHI, which is not me personally, might be able to say a bit more about that. There's recently there have been lots of different systems popping up, which are also becoming less and less expensive, and which all have a Wi-Fi connection and send you the data directly onto your cell phone. What I would recommend is to check for measurement accuracy and to possibly do a calibration. So even if you buy inexpensive sensors, you can still use them if you compare them to a high quality sensor that gives you what you might call a real result, a real temperature, a real relative humidity. And if you do that in the beginning of your measurement and depending on the type of sensor also in the end, you will get reliable results. Well, lots of details to take care actually if you want to make useful measurements. So difficult to answer that in detail. We did a small research project about how to measure passive house buildings, or generally how to monitor the energy efficiency of buildings. The results of which went into one of the protocol volumes of the Arbeitskreis for cost-efficient passive houses, working group cost-efficient passive houses, however you would like to translate it. This is available in German, and I'm not sure if parts of it have been translated and went into Passipedia.
Okay, thank you. Richard asks about, and I think he's referring to the supermarkets we saw. What type of refrigeration systems are used in those? Anything you can recommend? He asks about centralized ammonia systems.
Well, I never heard about ammonia systems being used in supermarkets. This refers to the refrigerant, I assume. In the old days, until 5 or 10 years ago, classic hydrofluorocarbons, R134A and so on, were being used in supermarket refrigeration, which are being phased out in the European Union for reasons of climate protection. So they have just the word doesn't come to my mind, but they are about more than 500, 1,000, 2,000 times more efficient in producing climate change than CO2 is. So currently, all centralized supermarket cooling systems are running on CO2 with quite good results also in terms of efficiency. And there's two different strategies you can follow. One is to really have a central cold production with, for example, a CO2 system, and you are distributing the liquid CO2 in the supermarket to the refrigerated cabinets, where it is evaporating, is cooling the cabinet, and is then returning to the central cold production facility. The other approach is to have small, decentralized refrigerators like you would have them in any fridge at your home, and have the waste heat moved out of the building if required by just a water circulation line. As it seems, the centralized systems are still being more efficient.
Okay.
Ammonia, just one word about that, is in principle a highly interesting refrigerant, but it is poisonous and it is also flammable, so it's much more difficult to handle, and there's much stricter safety requirements.
Okay, yeah, that's good to know. We have another question regarding the supermarkets, actually, from Louise. How do you deal with the big traffic of people, so people entering and leaving the building in regards to the energy efficiency?
We did some interesting experiments in a school where we wanted to know when there's like 500 students, and they are coming in the morning, and then they're going out for a break and getting back. How does that affect the energy balance? So we put up a large tent in the atrium of that school, covering the entrance, and then some volunteers were walking in and out through the doors, and we were measuring the amount of air they are taking with them. The result was that it is comparatively little air. So in a supermarket, you might see people are staying there for about 20 minutes. And on a typical day in the heating period, they would bring in a certain amount of air of, say, 10 to 20 cubic meters per person, which is about the amount of air they need for breathing, also for good indoor air quality in the supermarket, and which they can also approximately heat up by the waste heat from their bodies whilst they are walking around and shopping. So that in the end of the day, all these effects cancel out, and the calculation model for the supermarket just ignores the people, because in the energy balance, they produce as much heat and require as much air as they would also bring into the building. And this model works very well and gives good agreement with measurements, which have also been done.
That's interesting. Awesome. We have a question about the presentation, actually. Could you maybe put up the presentation again? It's referring to slide 22.
Yes, just a second. So as it seems, you can't see anything, although I can.
Yeah, well, we can also skip that one for now. Maybe.
Well, slide 22 was about the drain pipes.
He talks about a crossed out picture that was on the slide, and he wonders why it was crossed out.
Okay, yes. So that was, well, give me a chance to show it to everybody. Maybe it works now.
Yep.
So that one.
There you go.
Yes, that is what you would ideally do. So it is crossed out because in this case we don't have any adverse effects from the drain pipes on the energy balance because there is no air passing through the pipe. So the pipe is closed on top, and only if water is running down the pipe and is taking air with it and is creating an underpressure, then the valve, the white thing on top here, is opening and is allowing for air to get into the pipe, but then it closes again. So this is not what we are talking about here and which causes the problems and which needs to be considered in the energy balance, but it's those drain pipes that are opened on top and that are passing through the roof.
Okay. Perfect. We have a question from Daniel. Have you looked into the cooling capacity via the ventilation system? He clarifies, as far as he understands, if we do not humidify afterwards, the maximum load is 3 to 5 watts per square meter.
To be honest, I don't quite understand the question.
So
okay, so yeah, I know. If we are trying to cool a building only by the ventilation system, so assume you have a residential building with a typical air change rate of 0.3, 0.4 per hour, and you are cooling the incoming air. How much cooling capacity could you bring into the building? And the answer, in fact, is it is on the order of 3 to 5 watts per square meter. It can be a bit higher. You could get up to 6 or 7 watts per square meter, which is not very much. So a typical split unit would be designed to cover about 60 watts per square meter, so that it is able to quickly bring the room to a comfortable temperature once it is overheating and you get into that room. But in many cases, you can cool a building simply by cooling the supply air. And we did put quite some research into that, trying to find out are there comfort problems if you have small amounts of air but with a low temperature entering the room. And as it seems, this is not the case. So if you have a certain amount of energy you want to remove from the room, you can do that with small amounts of cold air or large amounts of not so cold air. And the variant with the colder air does not seem to be less comfortable than the other one. Instead, it creates less noise. But of course, the lower the temperature, the more you have to be aware of the risk of condensation. So you need to insulate all the pipes. And you may also need special valves where there is no condensation forming on the air inlet valve itself in the room. All this can be done. There are manufacturers that are providing specific air outlets for that purpose, but it's still a relatively rare system. And in many cases, even in the passive houses, a certain amount of recirculated air is being added just to get a bit more cooling capacity. And that can still be done as long as it's on the order of 100, maybe 200%. The ductwork doesn't get too big, the noise doesn't get too much. So that can also be an interesting option to distribute the cooling in the building.
Okay, thank you. Alexander asks, do you have any specific recommendations for monitoring systems inside passive wall assemblies?
Sorry, nothing special.
Nothing. Okay. Yeah, that was quick. Okay. We have another question from Daniel. He asks about the ventilation dimensioning of air quantities when calculating the design flow. Why is the PHBP multiplying the minimum flow with 1.3 and the CPHD training is not the material?
Okay, this is a pretty specific question. And generally about designing the airflow, I can say that you would design the airflow in a residential building depending on supply air requirements and exhaust air requirements. Supply air depending on the number of people who are there. Exhaust air depending on the number of kitchens and bathrooms. And that is a result that gives you a kind of a design airflow, and you can usually run the system with 70% of that airflow, and you should be able to have an slightly increased airflow rate. This is where the factor 1.3 comes from. For cases when higher airflow rates are required, if there's more people, if you are cooking whatsoever.
Okay.
Now, what exactly is in which slide of the CPHD
Yes.
training material? Sorry, I'm not able to answer.
Yes, of course. Okay, we also running over time a little bit. We have a question from Shane to say more about the outfit project. Maybe I can say a couple of words. I saw Georgia put in the website. We are also always releasing information through our newsletters and such. So keep your eyes open. So the outfit project looks into retrofitting of buildings with serial retrofitting. Sorry, and yeah, you can find everything on the website we have so far, and we're working on that to provide you with more information soon. So.
Yes, as George wrote in a sentence, passive house Energiesprong. So yes. the idea is to that we have large amounts of buildings in, well, for the case of Germany, that have been built after the war in the 1950s, 60s, maybe 70s, which are of extremely poor efficiency. Which were built because housing was required, and to a large extent, many buildings were needed to be built. And these are simple and can easily be retrofitted by prefabricated elements, or at least that's the idea, to measure the dimensions of the building, to prefab the new wall, including the windows and everything, the new roof elements, to bring them to the building site, and with a minimum of annoying the tenants within, say, 1 week or so, you would get a future-proof thermal envelope. And that's the main idea of the outfit project, to follow that path and to see where it takes us, and how that can be realized ideally at reasonable cost, and in any case taking care of all the detailed questions that arise if you really want to realize that. And of course we again want to get the connection to practice, to realize buildings, to real building projects, and that's where we are still looking for partners that might be interesting in doing such a pilot retrofit, and where we could provide our support in terms of research, knowledge, and communication.
Thank you. Thank you for elaborating on that. Prefabricated was the word that's slipping my mind. And I think this brings us to an end of today's webinar. Georgia also wants to say something about our campaign. Maybe you could do that right now.
Excellent, always happy. So first of all, thank you, Jürgen, for a fantastic presentation. Sorry to have missed a bit at the start of it, but as you said, old buildings in Germany are in need of retrofit, and I need a better internet connection as part of that. Nonetheless, I wanted to quickly mention, while we've got you all online, that iPHA launched our Global Efficiency First campaign last Monday. So together with all of our local affiliates on the ground, we are sharing a campaign together to bring out a joint message that we need to be thinking about efficiency first when we are designing new builds and, of course, retrofitting. So under the slogan, Efficiency, the First Renewable Energy, we'll be providing a range of campaign activities and events over the year. And the first one has already launched. We have the Explain Passive House competition, which will be on until next Monday. So if you've not participated yet, please do. There's a really great prize for the best description of how a passive house works. So you can choose from a PHPP expert course, a passive house designer course, or 2 tickets to this year's conference. So definitely be in it to win it. So that is it from me. We might have another campaign activity coming out next Monday, so keep your eyes peeled for that. And we look forward to receiving all of your entries to the Explain Passive House competition. back over to you, Carl, to conclude tonight's event.
Yes, thank you, Georgia. I also posted the link to the Efficiency First competition page of our website. And yes, I think that concludes our presentation today. Thank you, everyone, for joining. Thank you, Jürgen, for the excellent presentation. Thank you, Jessica, for monitoring the chat and helping us with that. And thank you, Georgia, for making it happen and logging on after all. And I hope to see you all soon.